Hello, this is Rick Nye. I'm a regional sales manager with Gefran. On behalf of our company, I want to thank you for tuning in today. Today I will be doing a technology overview on potentiometric linear sensors. If you have questions about what you will see today, you may email them to richard.nye@gefran.com. That's richard.nye@gefran.com. First, let's talk about what a linear position transducer is. A position or linear displacement sensor is a device whose output signal represents the distance an object has traveled from a reference point. It can either be an absolute sensor or a relative one. In the diagram below, the two blue dots each have an absolute distance measurement from a point that is defined as absolute zero. They also have a relative measurement between them. The dots could either be stationary or moving. The same concept holds for an angular sensor, measuring the degrees of rotation of an object with respect to a fixed point or axis. In this diagram, you will see that absolute zero is defined as true north. The red dot on the right has an absolute measurement of 120 degrees. The red dot on the left has an absolute measurement of 240 degrees. The relative measurement between them is 120 degrees. A linear displacement is a movement in one direction along a single axis. A displacement measurement also indicates the direction of motion. Usually this is indicated in millimeters or inches. A rotation is a circular movement of an object around a center or point of rotation. It can be in either direction. Angles of rotation are measured in degrees or radians. A position sensor converts or transduces the physical quantities such as millimeters, inches, degrees, or radians into an electrical signal such as amperes, volts, or digital output that is compatible with a data acquisition system. Examples of analog outputs are 0 to 10 volts DC, 4 to 20 milliamps, and many others. Examples of digital outputs are CAN Open, SSI, and Profibus. In a moment, we will dive deeper into potentiometric technology, but first, for comparison, I'd like to briefly talk about two other common types of linear technology, LVDT and magnetostrictive. First, we'll talk about LVDT. Many use the term LVDT universally to describe all linear sensors. This is not accurate. It is only one of the technologies used. Linear variable differential transformers, or LVDTs, operate on the principle of a transformer to measure displacement. The device consists of a primary fixed winding, blue in the drawing, that is powered by an AC power source, and two fixed secondary windings, red in the drawing. These primary and secondary windings are typically wound on a hollow form. In the middle of the hollow form is a movable core that is attached to the item to be measured. When the movable core is centered with the primary and secondary windings, as shown in this picture, the voltage induced in the secondary windings is of equal magnitude but 180 degrees out of phase, and thus cancel. This would indicate a linear measurement of zero. Moving the core left or right induces a greater voltage in one of the secondary windings than the other. The difference, or differential, in the voltages represents the linear measurement. This is why the device is referred to as linear variable differential transformer. Advantages of this technology. It is robust because the movable core does not touch the coils. Since it is based on an electromagnetic coupling, the resolution is infinite, or limited only by the data acquisition system. Disadvantages. Due to the core within a tube design, form factors of the sensor are limited. Being electromagnetically coupled, the device is sensitive to electromagnetic interference. Temperature affects performance. Because of the above disadvantages, LVDTs are used less commonly now than magnetostrictive and potentiometric sensors. The next type of linear technology I'd like to talk about is magnetostrictive. A magnetostrictive sensor consists of a transmitter, shown in black with a gold band in the picture, which sends a pulsed signal down a tubular waveguide. This produces a circular magnetic field around that waveguide. A cursor magnet slides up and down the length of the sensor, creating a reflected torsional wave that travels in both directions. In one direction, it goes to the damper and is damped so that it will not reflect back and interfere with the measurement. In the other direction, it heads toward the receiving coil. The sensor electronics measure the time difference between the emitted pulse and the return wave picked up by the receiving coil to determine the length. There are numerous advantages to magnetostrictive technology. First, there are many form factors. It too has infinite resolution. Due to the built-in electronics and amplifier circuits, there are a wide range of analog and digital outputs. They're robust. They have a long life because they are touchless. They have the capability of multiple cursors and to measure distance between multiple cursors. They can measure speed in addition to length. There are disadvantages to magnetostrictive technology. They are more expensive than potentiometric. They are susceptible to EM interference. This, however, is nearly eliminated by Gefran hyperwave technology. I will be doing another technology overview focused entirely on magnetostrictive linear transducers in the coming weeks. Gefran is also a leader in two other technologies, Hall effect and MEMS capacitive. Gefran has developed a method of using Hall effect in a perpendicular fashion so that it can be used to measure rotation angle. Gefran also uses MEMS capacitive to measure inclination and tilt. These are outside the scope of this discussion, and so I will not go into further detail here. For the remainder of this presentation, I will be talking about potentiometric linear technology. A potentiometer is an electromechanical device that provides a voltage variation value by a ratiometric electrical signal proportional to the measured displacement using the absolute position of the shaft or cursor. The potentiometer main elements are the board with a resistive track and a collector track, shown in green and black in the picture, and the wiper with the different contact brushes that slide the length of the board and connect the tracks. Here we see a representation of a linear transducer with rod. The output voltage varies with the extension of the rod across the full theoretical electrical stroke. When the rod is fully retracted, the output voltage will be 0. When the rod is fully extended, the output voltage will be equal to the supply voltage. The output voltage will be linear between those two extremes. When the rod is 50% extended, the output voltage will be 50% of the supply voltage. This technology is said to be potentiometric because we are measuring a potential difference by comparison to a known voltage, which is the supply voltage. It is said to be ratiometric because the output voltage is in a direct ratio to the measured length. This type of sensor is also referred to as a voltage divider. The ratio of the output voltage to the supply voltage is equal to the ratio of the measured length to the max stroke length. Now I will talk about different design considerations, starting with stroke. Here you see a section of the datasheet for our LT series transducer. The model number is indicated by the useful electrical stroke in millimeters. This is the darker top line. Beneath that you will see 3 stroke lengths referenced: useful electrical stroke, theoretical electrical stroke, and mechanical stroke. It is important to know the difference when designing in one of these sensors. In this diagram, you will see the 3 stroke lengths represented. The mechanical stroke is the maximum mechanical travel possible from the point that the limiter nut is firmly against the sensor body to the point of maximum possible extension. The theoretical electrical stroke is just inside that on both ends and represents the range across which the output voltage will go from 0 to the supply voltage. At the extreme ends of this range, the output will not be linear. The useful electrical stroke is just inside of the theoretical electrical stroke and represents the range where the output is linear. It is this range that should be considered against the object to be measured. Here we see an electrical representation of this. All potentiometric linear transducers are 3-wire. In this diagram, the supply voltage is across pins 1 and 3. Pin 2 is the measured output. The resistor shown in the drawing represents the length of the supply and collector tracks in the sensor. Above that, the curved line represents the wiper in the sensor. In this representation, you will see how the different stroke lengths are related. The useful electrical stroke is fully inside the theoretical electrical stroke to eliminate the tiny nonlinear regions. Best practice when calibrating the transducer is to be careful to set the stroke so that the output does not drop below 1% or rise above 99% of the supply voltage. This will ensure you stay in the linear range. It also defines a voltage slightly higher than 0 to represent a measurement of 0 length. In this way, the control system can determine the difference between a measurement of 0 and a loss of signal. The next design consideration is linearity. The linearity is the measure of the proportionality between the actual values of a variable being measured to the output of the instrument over its operating range. The measured curve in the image presents some traits of nonlinearity with respect to the ideal curve, which is actual values. Typically in these sensors, it is very low at only plus or minus 0.05%. The next design consideration is resolution. The resolution of a potentiometric linear transducer is infinite because the device is a simple voltage divider and does not have an amplifier circuit or a digital converter. Resolution of a system will be limited only by the electronics of the control system, whether a discrete controller or a PLC. In these pictures, you'll see a picture of our PC series transducer. The resolution on this transducer is infinite. You'll also see a picture of our 2500 series controller. Although it is very, very good, the resolution is not infinite. The specification on the analog inputs are an accuracy of 0.1% for full scale, sampling of 2 milliseconds, and a resolution of 100,000 steps at 2 milliseconds. The next design consideration is actuator type. Potentiometric linear transducers are typically available in one of two actuator types, with rod and rodless. If a transducer is selected with rod, the application must be able to accommodate the full length of the sensor body plus the full extension length of the rod. In rodless designs, the mechanical travel is within the length of the sensor body, so it is more compact. Other design considerations include reliability and life, magnetic interference, and temperature. Although potentiometric linear transducers have wipers that slide on conductive tracks, the lifespan is still high, typically 25 million meters covered by the wiper or 100 million translations. Potentiometric linear sensors are acceptable to use near magnetic fields or in areas of high electromagnetic interference. The working temperature range is typically from -30 to +100 degrees C, and the storage temperature is typically between -50 to +120 degrees C. Now I'll talk about how to select the right potentiometric sensor. This includes choosing the desired electrical connection type, choosing the most suitable mounting method, ensuring the correct level of protection from solids and water, and selecting the sensor with the right stroke length and form factor for your application. Choosing the correct electrical connection type. Common electrical connection types include 3, 4, and 5-pole connectors and 3-pole cable outputs. Since potentiometric linear sensors are 3-wire sensors, the 4 and 5-pole connector outputs will only use 3 of the pins. Available connectors and pin assignments are all clearly defined in the data sheets for each individual sensor. Mounting methods. There are 3 main types of mounting methods for linear transducers: brackets, flange, and self-aligning ball joints. Ingress protection. When looking at specifications, you'll see IP60, IP65, or IP67. So what does that mean? The first letter I stands for ingress. The second letter P stands for protection. followed by two numbers. The first number indicates the protection against solids, and the second number indicates protection against water. First, let's take a look at the first number, which is the protection against solids. If that number is a 0, it means no protection against ingress of solids. If it's a 1, it's protected against ingress of large objects, greater than 50 millimeters. If it's a 2, it's protected against objects greater than 12.5 millimeters, like fingers. If it's a 3, it's protected against objects greater than 2.5 millimeters, like tools. If it's a 4, it's protected against objects greater than 1 millimeter, like wires, nails, screws, insects. If it's a 5, it has partial dust protection, meaning dust may enter but should not interfere with the operation of the device. If it's a 6, it's dust tight or vacuum sealed against continuous airflow. The second number indicates protection against liquids. If it's a 0, it has no protection against any liquid penetration. If it's a 1, it's protected against vertical dripping water. If it's a 2, it's protected against water droplets deflecting up to 15 degrees from vertical. If it's a 3, it's protected against water spraying up to 60 degrees from vertical. 4 is protected against water splashing from any direction, tested for 10 minutes using an oscillating sprayer. 5 is protected against low-pressure water jets from any angle. 6 is protection against direct high-pressure jets. 7 is protected against immersion up to 1 meter for 30 minutes. 8 is protected against extended immersion at greater depths and pressures. 9K is protected against high-pressure jets, high temperature, washdowns, or steam cleaning. So what does all this mean for linear transducers? Not all linear transducers have an IP rating. It is not always necessary. Most of our linear transducers fall into 3 IP ratings: IP60, IP65, and IP67. IP60 is dust tight but has no water protection. These are not for outdoor use unless fully enclosed. IP65 is dust tight and is rated for nozzle projected water. These are suitable for outdoor use, but we recommend applications that provide some additional protection. IP67 is dust tight and is rated for water immersion. These are suitable for outdoor use, extreme weather, and flooding. Now we will discuss selecting the right stroke length and form factor. Gefran is the world's largest producer of potentiometric linear transducers. This is a picture of our potentiometric product offering. As you can see, there are many different sizes and styles to select based on your application. We will now look at some of the options for stroke and form factor. Gefran divides our potentiometric linear sensors up into 4 main categories: long stroke models with measurements up to 2 meters, short stroke models with measurements up to 300 millimeters, magnetic drag models with measurements up to 1 meter, and exposed track with measurements up to 550 millimeters. Magnetic drag and exposed track styles can be used inside of a pneumatic cylinder. We'll go over all of these in more detail. First, let's look at some examples of long stroke sensors. The LT series has a profile body shape, is bracket mounted, and has an extendable rod. It can measure up to 900 millimeters. It is the simplest, most sold, and most copied of all of our models. It is ideal for plastic and rubber injection presses, vertical presses, and many other processing machines. The LT model is available in either IP60 or IP65, and the LT67 model is rated IP67. The PC series has a profile body shape and mounts with self-aligning ball joints. This allows it to measure distance between 2 points that are moving at compound angles to each other. It can measure up to 750 millimeters. The PC model is rated IP65. The PC67 version is IP67. This type of sensor is great for measuring steering angle on agricultural and construction equipment. It has a 10 millimeter steel shaft and is reinforced for those types of applications. It is also ideal for metalworking, woodworking, and ceramics. The PK series is a rodless design, so the full travel is within the sensor body. It is bracket mounted and is our longest potentiometric sensor, with the ability to measure up to 2 meters. Rodless designs also avoid the pump effect that can happen in longer sensors with extendable rods when the rod travels very quickly. This style is used on plastic and rubber injection molding machines, vertical presses, and many other processing machines. It is rated IP40. Now we will look at some examples of short stroke models and smaller form factors. The PA1 is space-saving and measures up to 150 millimeters. It can handle high speeds and is very resistant to shock and vibration. This model is ideal for small mechanical devices, valves, tools, and test benches. The PZ series is our most versatile series. They have a cylindrical body ranging from 1/2 inch to 3/4 inch in diameter. They are available in all 3 mounting styles: bracket mount, flange mount, and self-aligning ball joint. The applications for these are numerous. These are examples of touch-style sensors. They are used when it is not practical to affix the rod to the item being measured. They are available with different touch tips and rollers for engaging the item. They are space-saving and double-supported since the control rod passes completely through the sensor body. The PY1 model has a ball joint for allowing higher movement. This is ideal for small mechanical devices, valves, tools, and testing equipment. The PY2 and PY3 models are spring return. They are ideal for checking flatness or thickness of materials. They can also be used to measure the depth of a blind hole. All of these are bracket mounted. Magnetic drag sensors have a sliding outside cursor that magnetically drags the internal measurement cursor. This design allows for a high IP rating of IP67. They are typically for in-cylinder linear measurement. Examples of this include our PME model. It is a cylindrical sensor designed for humid environments. It has an anodized aluminum body and can be used in compressed air environments up to 20 bar. The PMI model is designed for use inside oil pressure cylinders, which requires high strength. It has a stainless steel body and can work continuously in pressures up to 250 bar. It has internal flanges or external threads to guarantee mechanical compatibility with all principal cylinder types. The PMA model is similar to the PME, only with self-aligning ball joints. It comes only with cable output and is ideal for utility vehicles, construction equipment, agricultural equipment, or any application where the angle of the drive axle changes constantly. These sensors are designed solely for in-cylinder use. The IC model has exposed tracks and a slim design for use in narrow pneumatic and hydraulic cylinders. It is flange mounted to the cylinder. The PMI SL and SLE are variations of the PMI model that are designed for all inside cylinder applications which require a smaller transducer. For this reason, the diameter has been reduced to 12.7 millimeters. The SLE version has an amplifier circuit and provides a 4 to 20 milliamp output. They are available in flanged or threaded versions to accommodate all main cylinder types. Signal conditioners. Potentiometric linear transducers are simple 3-wire voltage dividers with voltage outputs ranging to 60 volts. If amplified and conditioned outputs are desired, we offer signal conditioners. The PCIR signal conditioners have been designed to enable the user to adapt the output impedance of linear or rotative displacement transducers in conductive plastic for acquisition systems or PLCs in a way that does not alter the linearity of the transducer output. The output is 0 to 10 volts DC. It is DIN rail mounted and can be connected simultaneously to 2 transducers. The PCIR 101 and 102 take the ratiometric output of our potentiometric transducers and convert it to amplified conditioned output. The PCIR 101 provides a 0 to 10 volt DC output, and the PCIR 102 provides a 4 to 20 milliamp output. The circuit is integrated in a 4-pole connector and has trimmers for zero and span. Next, we will take a look at where some of these types of sensors are installed. They are used to measure the opening and closing of molds in injection molding machines. Our long stroke sensor styles LT or PK are ideal for this, depending on the stroke. These sensors are used in metalworking, calendars, and bending sheet metal. Machines that bend sheet metal use 3 to 4 calendars. Position sensors are necessary to measure the position of the calendar rollers to control the separation and parallelism with high precision. Long stroke models like the LT, PC, and PK, touch style like the PY2, and short stroke models like the PZ are ideal for this application. They are used in woodworking and sanders. Sanders reduce the thickness of the panel by means of longitudinal abrasive belts. It is important to check the position of the rollers and the belt tension. This requires a sensor with a high IP rating. Solutions include our PZ, PY, and PZ34 short stroke sensors. Materials processing like grinding, polishing, thickness control. Machines that grind, polish, screen print, cut, or seal all require a check of the position of the specific tool or grinding wheel. Solutions for this include long stroke models like the LT or PC, short stroke models like the PA1 or PZ, or touch style models like the PY. They are used in geotechnical applications for structural health monitoring. For structures like bridges, dams, and monuments, it is important to monitor the condition of the structure and to check for cracks and shifting. Cylindrical potentiometric linear sensors are perfect for this because of their small size and high IP rating. Magnetic drag models like the PME and PMI, and short stroke models like the PZ12, PZ34, and PZ67 are ideal for this type of application. They are used in mobile hydraulic applications like utility vehicles. On utility vehicles, there are many places where these sensors are used, such as controlling the compactor and raising and lowering of lift arms. These applications sometimes involve inside cylinder solutions. Magnetic drag styles like our PMI and PMI SL are ideal for this. They are used in mobile hydraulic applications such as agricultural equipment, construction equipment, and aerial lift. Applications include pedal control, steering control, vehicle inclination, cabin positioning, cylinder position, arm extension, boom extension, basket extension, vehicle stabilization control, and farm implement positioning. The applications are numerous. Solutions include long stroke solutions like the PC and PC67, and magnetic drag solutions like the PMA, PMI, and PMI SL. In conclusion, potentiometric linear transducers use simple electronics. They're inexpensive, robust, have a long life, great linearity, come in many form factors, have a wide temperature range, they're immune to EM interference, they have high IP ratings, and are suitable in a wide array of applications. I want to thank each and every one of you for giving us your time today. We hope that you will consider potentiometric technology, and we hope that you will consider a Gefran solution. Our sales and engineering team would be glad to assist you with your applications. If you have questions about what was presented, or you have an application you'd like to discuss, please email me at richard.nye@gefran.com. That's richard.nye@gefran.com. Thank you.